If you think of the little molecules flying around in the chamber, if the chamber is bigger and those molecules have more space to run around in, they have more options available to them. It's more random for them to be spread out over the bigger space. There are alternative ways of thinking about the microscopic details of entropy. The second law of thermodynamics is just a statement of probability. Just a statement of the probability. It's a coupling law of nature. And let me give you a concrete example so that we can think about it. Suppose I have a deck of cards. You buy it and it comes highly ordered. When you buy it from the store, you take off the plastic. It is ace through king of the one suit, ace through king of the next suit, and the way for all four suits. It is ordered. You can predict by looking at the one card what the next card will be. That's a part of what you mean by the orderly system. If you were to now shuffle that deck, or just drop them on the floor or pick them back up again, if you do something with the deck, then they will become more random. That's what spontaneously happens, and that's the second law of thermodynamics. The second law of thermodynamics says, if you just let system evolve and if they are isolated, then as time goes by, either the entropy will stay the same or it will grow bigger. Things become more random over time, but they won't spontaneously decrease in entropy. If you take that deck of the cards and you don't shuffle it at all, there is no change in the entropy. You can sit there and hold it, and you can move the deck around without mucking up the order. Entropy doesn't have to increase, but as soon as you shuffle it, with the first shuffle the entropy increases somewhat. Now it is much more difficult to predict what the next card will be from the previous one. If you look carefully after one shuffle, you will still see some order, but it will be a little pattern or such as 2, 3, 4, and then 8, 9, and 10. After a couple of shuffles, it's really random, and from then on the shuffling, more and more won't increase randomness. It's already fully shuffled, but what won't happen, this is a second law of thermodynamics, what will never happen in your lifetime is that you take a random deck, shuffle it, and you look at it and go, ace through king of the spade, ace through king of the clubs in order. It's not going to happen. Why won't it happen? Well, because its probability is insanely unlikely to happen. You can count how many states are available with 52 distinct cards. How many different orders are there? Yeah, it's a probability, right? That's a fun little statistical calculations, and you can write it down. There are lots of zeros in the answer to that question, and the probability that randomly ordering will put it into this ordered state is basically one out of all many possibilities. Only one is the ordered state, and so the probability of that happening is 1 out of this astronomically huge number, right? It's so improbable. It's so improbable as to be practically impossible. Now, that's a case with 52 cards. If we go to the one extreme and we only had a couple of cards such as simply ace, 2, 3, and 4, and you shuffle them, it's going to be more random, maybe ace, 4, 2, and then 2, 4, 3, ace. If you shuffle enough times, sooner or later you might be back to ace 2, 3, 4, because there are only 4, so the probability is small, but it is certainly not 0. With 52, you could shuffle once per second for the rest of the lifetime of the universe, and it's not likely to happen. Yes. Now imagine going not from 4 to 52, but from 4 to 52 to a million, billion, trillion, because that's a pot of water, the thermal motion, the random motion of the molecules is really shuffling the deck. It's shuffling the ordering of the molecule in the water, and now instead of 52, you have a million, billion, trillion, and the number of states available, just as the number of states is much more than the 52. There are not 52 configurations of the cars, there are billions of billions, and the number of configuration of the molecule is an insanely large number. If you try to write it down, you could start writing zeros and walk all the way to the edge of the universe, and you would not be done yet. What is the probability that those will go into the more ordered state? The answer is 0. That is the second law of thermodynamics. If you think about this, you can realize that this really is connected with the way we were thinking about the second law of thermodynamics, which is Mr. Carnot's arguments. The first statement that I made was that the thermal system, when they are isolated, always tend to go from hotter things to colder things, and from colder things to hotter. I can understand that if I'm thinking about entropy, because spontaneously if the colder things kept growing colder and colder, it would be more and more orderly. It would go to the perfect order if that kept on happening. Now, it is true that the hot things would be more and more random, and so you might ask, well, could the increase in the entropy of the hot things more than the balance the decrease in the entropy of the small thing? It becomes a technical counting story. You have to think about how many states are available. It depends on the temperature, and what you discover is that the Carnot is absolutely right. Wow. It's a pure mathematics. It is a derivable. It is a derivable. Okay? So, once you think about thermodynamics in this way, once you think about the second law as a statement about systems and their natural evolution, you realize that there is an energy and there is an energy. Some energy is more useful than other forms, and what do I mean by more useful? Now we can be rigorous. More useful energy means less entropy. If you have some material that has energy stored and that energy is very orderly, for instance in the automobile that is traveling down in the highway, every molecule is going in exactly the same direction with the same average speed. It's the speed of the car that's about as orderly as you can have it, and that's a very low entropy state for that amount of energy to be configured in. Wow. So, what's going to happen over time? Well, spontaneously that car might crash. If it crashed, then that energy would be conserved, but it would now be random thermal energy. The car is stopped, and now the molecule jiggle faster. You have taken that the same amount of the energy, and it is spontaneously turned into a more random distribution. That's the way things go. Wow. What never happened in nature is it's the second law of thermodynamics is that a car crash spontaneously undergoes itself the metal reform into the more orderly care, and then all of the thermal energy from the crash is conserved to the kinetic energy of the car. No, it won't happen. That's the second law of thermodynamics. Yes. Once you understand this, you recognize why there is a maximum efficiency for an engine. Yes. Imagine that you have the hot gases in your automobile engine, and so you have some energy in there. Every molecule jitters around fast. There is plenty of kinetic energy. If only you could extract the energy and put it into your car instead of it being random in the molecules, that would be great. That would be how you would drive your car, and you can do that. That's what the car engine is doing. But you cannot take all of the engines. You cannot take all of the energy and put it into the motion of your car, because that would violate the second law of the thermodynamics. Think about it. If you started this purely random energy, it has high entropy, and if you could somehow convert it all into the kinetic energy, then you have just radically decreased the entropy of your automobile. Wow! You started off with a high entropy, and spontaneously, through some workings of the magical engine, convert it into the low entropy system. It's never going to happen. There is no such a magical engine. Right, be realistic, please. Yes. So the second law of thermodynamics says you have that energy and you cannot convert it all into the mechanical energy. You have to throw some of it away, increasing the entropy of the cold bath, and that will increase in entropy enough to cancel the small decrease that you have by also ordering the molecule in the car. There is a balancing act, and the second law of thermodynamics tells you that quantitatively how much the best balance is that you can have. That is Mr. Carnot's original formula, where he wasn't thinking about randomness. He was just looking at the steam engines themselves. Interesting. There is a very common misconception about the second law of the thermodynamics. Many people misled it, and they miss that caveat for isolated system. If you don't read that, then you say, oh, the second law of the thermodynamics say that entropy can never decrease. If you saw that it is what the second law of thermodynamics says, then you would become very confused, because if I handed you a deck of cards that was random, and you sit down and for a few minutes, you can order them. You can decrease the entropy of the deck of the cards, and you would say, is that a violation of the second law of thermodynamics? The answer is no. It took some work, yes. The cards are not an isolated system. They are not spontaneously reordering. You need to do some work on them. You can locally decrease entropy, put the water in the freezer, and they will spontaneously, by themselves, without you doing anything further, become colder and colder, and then would freeze. As they become colder, they are becoming less entropic, less random, and when they freeze, the entropy is going down even more. Now they are very ordered. There is a crystal. If you know where one molecule is, you know right where its neighbor is. It's very orderly states. Did that happen spontaneously? Well, yes and no. Inside of the freezer, it happened spontaneously. But look at the system that it's part of. You have to plug the freezer into the wall for this to happen. If you don't plug the freezer in, it's not going to just happen by itself. You need some external energy, which is electricity. Some people have argued that human beings are low entropy states because we are very ordered. We have organs that are separated, and if you think about the chemicals that made up your body, if those chemicals were all randomly separated, they would have much higher entropy. That is correct. And when your mom made you, when her body created you, she was taking the chemicals and ordering them into the shape and form of human body. Right. Blastomere. Entropy was decreasing in your location, but mom was eating. She was metabolizing. She was consuming energy from an outside system, and she was throwing away a lot of waste heat. In fact, she was warming up the environment that she lived in, vastly increased the entropy of her surroundings, order of the magnitude more than the degrees that you represented. Yes, you can decrease entropy here as long as you increase it somewhere else. So that the sum total is always going up and up and up and up. Now, this has led some people, philosophers largely, to think about time. Time is connected to the story because as time goes by, entropy is increasing, and the people have often puzzled about why. How do we think about the time always moving forward? The arrow of time points in the one direction. The future is very distinct from the past. If you look Newton's law, you don't have any clue about why time should go one way and not the other. Think about watching a movie of the billiards. Perfect Newtonian motion. They come in, they interact, they go back out again. Conservation of energy, conservation of the momentum. You cannot tell if they are running forward in time or if you run the movie backwards and they are going backwards. Both look perfectly reasonable. Newton's law don't seem to tell us which way time should go. But if you watch something more complicated, something where the thermodynamics is involved, as if you drop an egg, it hits the ground and smashes. You know very well that if you run that movie backwards that you are looking at nonsense. Eggs don't spontaneously start in this random, mashed up state. It takes energy from the floor, cooling the floor, and a little bit to take that energy to reveal the chemical bond to make an eggshell. Oh, and let's use a little bit of that going into the form of kinetic energy to make it fly up into your hands. It won't happen. The arrow of time points in the direction of the increasing entropy. Just a fun philosophical point to think about when you are thinking about this entropy story. In the end, we have a new law of thermodynamics. It's important. You cannot understand heat engine if you only think about energy conservation. You have to think about entropy and randomness, or the second law of the thermodynamics, in order to fully understand the complexity, reality, and ordinary behavior of any thermodynamic system. Thank you.